You know, when you think about complexity today, it's everywhere, isn't it? Biological systems, cities,
Yeah,
technology.
absolutely. It's a huge challenge just trying to grasp how all the pieces fit together.
Right. How do they influence each other? How does the whole thing actually work? It's not just the sum of the parts.
Exactly. It's easy to get bogged down in the details and miss the bigger picture. We tend to break things down, which helps. But yeah, systems are dynamic.
And seeing that whole picture, that's what we're digging into today. We're looking at this really interesting connection point
hmm
between a way of thinking about complexity systems thinking and a very hands-on visual tool called LabVIEW W.
Yeah, and for this deep dive, we're mainly drawing from an article, The Flow of Thought, by William L. Weaver. He's got decades of experience teaching this stuff. We're also pulling in some related ideas from other sources, but Weaver's perspective is central.
Okay, so what's the mission here? It seems we're trying to unpack how LabVIEW in its actual design doesn't just let you build systems, but it almost seems to inherently teach systems thinking. Like, it embodies the principles, especially around visualizing the flow of energy, material, and information, EMI.
Precisely. It's about finding those aha moments where the connections just click because you can see them in the tool.
Okay, so before we get into LabVIEW itself, let's lay the groundwork. What exactly is systems thinking based on the source?
Well, fundamentally, it comes out of general systems theory. It's really about understanding the whole system, the interactions, the relationships, not just looking at the pieces in isolation.
So it's a perspective shift, away from just parts towards connections.
Exactly. And the article points to a few core principles. First is holism, the idea that, the system's behavior emerges from how the parts interact. It's more than the sum of its parts.
Like a flock of birds, you can't predict its movement just by studying one bird alone.
Perfect example. Then there's interconnectedness. Everything's linked. You change one thing, and the effects can ripple right through, so you focus on those dependencies.
Nothing happens in a vacuum, basically.
Pretty much. Third, feedback loops. This is huge for understanding dynamics. Outputs circle back and influence inputs.
Right, so things can regulate themselves, like a thermostat.
Or they can amplify, leading to growth, or maybe even collapse. It's about circular cause and effect, not just straight lines.
Much richer than simple A causes B.
Definitely.
Yeah.
Fourth principle, emergence.
Hmm.
This is where new properties pop up at higher levels that you just couldn't predict by looking at the lower level components, like consciousness emerging from neurons.
Something genuinely new appears from the interaction itself.
Yes. And lastly, boundaries and environment. You have to define what's in the system and what's out, and crucially, how it interacts with its surroundings, especially through those flows of energy, material, and information. EMI.
Got it. So systems thinking gives us this toolkit, this lens, to see patterns and structures that simple cause and effect thinking might miss. Now, link this to LabVIEW W.
Okay, this is where it gets really interesting. Weaver points out something striking. LabVIEW W's architecture seems to naturally mirror these very principles. It's almost like it was designed with systems thinking in mind, even if indirectly.
Okay, so how? What's the first parallel?
Well, think about that basic systems thinking model. The box. You have inputs, some internal process, and outputs.
Right, the classic black box idea sometimes.
Exactly. Now look at LabVIEW's fundamental unit, the virtual instrument, or BS6. It's an operational version of that system box. Graphically, it even looks like a box its icon.
Okay.
It has defined inputs, called controls, and defined outputs, called indicators. You see these on its front panel, which is like the user interface.
It's what you interact with.
Right. But the key bit is the connector pane. This acts like a very strict boundary. It maps those controls and indicators to terminals, defining exactly how data representing EMI flows in and out when you use this VI inside another one.
So it enforces that input-output boundary.
Precisely. It makes the black box concept real and usable. You can use a complex function just by knowing its defined interface, without needing to dive into its internal workings every time, essential for building anything complex.
Makes sense. Okay, what's next? You mentioned flow, EMI flow.
Right. System thinking stresses how energy, material, and information flow creates causal links. And LabGW's core execution model, the data flow paradigm, is a direct parallel here.
Data flow. How does that work?
Unlike a lot of text code that runs line by line, in LabVIEW, a node, which could be a match function, a sub-VI, anything only runs when all of its required inputs have arrived through the wires connected to it.
So the wires aren't just visual lines. They actually carry the data and dictate when things happen.
Exactly. It's not just a picture of the flow, it is the executable logic. The visual layout determines the dependencies and the execution. Data flows along the wires, representing information, often from measurements, triggering the next process. Your LabVIEW program becomes this dynamic map of EMI interactions.
Okay, that's a big one. And just like systems thinking uses diagrams.
The LabVIEW block diagram is that system map. It's literally a visual network of nodes connected by wires showing data paths. It makes the structure, the dependencies, even how memory is managed visually explicit.
Wow.
Weavers even notes how similar these diagrams can look to, say, causal loop diagrams or even simplified neural nets. And because nodes run when data is ready, not in a fixed sequence, LabVIEW naturally handles parallel processes, things happening at the same time, which is common in real systems.
So the map is the territory, in a way. The visual structure is the working system. Okay, keep going. What about breaking down complexity? Big systems.
Systems thinking talks a lot about modularity and hierarchy, breaking big systems into smaller interacting subsystems. Herbert Simon's idea of nearly decomposable systems fits here. Modules that interact strongly inside but have weaker links between them makes things more robust.
And LabVIEW does this with?
With subvis.
Yeah.
A subvis is just a ZV that you use inside the block diagram of another Cs. It's like nesting boxes.
Okay.
Each subVI encapsulates some piece of functionality.
Yeah.
It has its own icon and that connector pane interface we talked about. So you build complex things by combining these smaller, focused, reusable modules. It's hierarchy in action. A good sub-VI is a nearly decomposable module. It makes big applications way more organized and easier to maintain.
That maps really clearly. What about those dynamics, the feedback loops?
Crucial for system behavior. LabVIEW has specific structures for this. There are feedback nodes, which basically remember the value from the last time a loop ran. A one-step delay, kind of.
Like a memory of the previous state.
Exactly. And then there are shift registers, which pass data from one loop iteration to the next, so you can maintain state or information across the entire run of a loop.
Ah, so you can build things that change over time based on past results.
Precisely. These are the building blocks for iterative algorithms, difference equations,
Yeah.
the math behind dynamic modeling.
Yeah.
And when you think about control systems like PID controllers used everywhere in industry, they fundamentally rely on implementing feedback. LabVIEW is used extensively for control because you can wire up these feedback structures, connect them to real-world sensors and actuators, and the code becomes part of that physical feedback loop. And visually, you literally see the wire looping back on the diagram. Makes that circular causality crystal clear.
That's powerful, seeing the loop in the code that controls a real thing. What about visualization more generally?
Both systems thinking and LabVIEW lean heavily on visualization and abstraction. Systems thinking uses diagrams, like causal loop diagrams, to make complex relationships easier to grasp. LabVIEW, well, it's inherently visual programming.
Right. The block diagram is the code, the front panel is the interface.
And the icons for functions and sub-VIs are abstractions. They hide the inner workings. But the critical thing, again, is that the diagram is the code. It's not just documentation. It runs. This creates this dynamic learning environment. You can easily zoom in on a sub-VI icon to see its detailed logic, then zoom out to see the big picture.
Managing complexity at different levels.
Exactly. It really lowers the cognitive load, especially if you're a visual thinker.
Okay, one more major principle. The holistic view, the big picture.
Yes, systems thinking is all about seeing the interconnected whole. LabVIEW, being an integrated development environment, or IDE, kind of nudges you in that direction. It supports the whole life cycle in one place. Simulation, connecting to hardware, acquiring data, analyzing it, displaying it.
So you're forced to think about the entire process.
Pretty much. If you're building, say, a test system, you have to consider the sensors, the signal conditioning, the processing logic, and LabVD, the user interface, how data is logged, the whole chain from the real world and back.
Yeah.
It naturally encourages that end-to-end perspective.
Plus, you can quickly prototype and change things.
Right. Its rapid development capabilities support an iterative, adaptive approach, which is also very much in the spirit of managing complex, evolving systems.
It really is a striking set of parallels, and the source emphasizes this isn't just theoretical, it's powerful for teaching these ideas.
Yes, absolutely. Weaver's 25 years of experience really comes through here. He sees LabVIEW as a profound pedagogical tool for making systems thinking, and that EMI framework truly tangible for students.
How so? What does it do for learners?
Well, first, abstract concepts become concrete. Feedback loops aren't just diagrams. Students build a VSI, maybe a simple temperature controller, run it, and see the simulated temperature stabilize because of the negative feedback they implemented. They experience it.
You're not just reading about it, they're doing it.
Exactly. Second, it makes visualizing those EMI pathways explicit. Students design systems where, say, a sensor input, measuring something material or an energy level, becomes data, gets processed into information by their LabVIEW code, their model, and maybe leads to knowledge displayed or an output signal controlling something. That whole transformation chain is laid out visually on the block diagram.
They're literally drawing the path from measurement to understanding.
And this reinforces something called the universal measurement model. When they build a data acquisition system, they have to think about what's the environment, what data am I measuring, what transducer sensor do I need, how do I get the information signal, what model processing do I apply in my code, what knowledge do I get out. Each step becomes an active design choice within LabVIEW.
That sounds like a very structured way to learn scientific observation itself.
It is. It also builds crucial problem-solving skills. That's sub-BI architecture. It forces students to learn modular design, break down a complex problem like automating a lab experiment into smaller, manageable, testable chunks. That's a fundamental skill in engineering and systems analysis.
And that interconnectedness idea, does the tool reinforce that too?
Oh, definitely. The data flow paradigm hammers it home. A function block won't run until its inputs are valid. Students learn visually and immediately that components depend on each other. They have to wire things correctly. The flow must work for the system to function. Debugging often becomes about tracing that flow to find the break.
The tool itself enforces the system's thinking.
It really does. And the last point Weaver makes, which is powerful, is fostering education as agency. Instead of just passively receiving information, students are actively designing, building, testing, debugging their own systems. They learn to think like system designers, to troubleshoot, to innovate. It shifts them from being trained to being empowered.
Okay, so wrapping this up, the convergence is pretty clear.
Yeah, the parallels are striking. It's like systems thinking offers the conceptual language, and LabVIEW provides an executable language for tackling the same challenge, managing complexity. LabVIEW creates this space where systemic principles aren't just ideas on paper, they're embedded in how you build and run things.
A bridge between theory and practice.
A very direct bridge. For anyone trying to get their head around complex systems, science, engineering, doesn't matter. LabVIEW seems to make systems thinking much more accessible, concrete, and frankly, impactful, especially for visualizing that EMI flow. You're graphically building the flow of thought, the flow of data.
Empowering people with that holistic view and the skills to actually build and analyze.
Exactly. The perspective and the agency to tackle complex challenges.
This has been fascinating. It really highlights how a tool, even one built for engineering, can embody such a deep philosophical framework.
It speaks to the universality of the principles, I think.
So here's a final thought for you, the listener, to maybe chew on. Think about how a tool designed for a specific practical purpose like engineering could fundamentally alter how we learn and even think about complex systems in general. Does using something visual and data flow driven like LabVIEW actually shape our cognitive approach? And are there other tools out there, maybe in completely different fields, that similarly embody powerful ways of understanding complexity, perhaps in ways we haven't recognized yet? Something for you to ponder.